Hello everyone, my name is Thêm Lee and I want to become a physics teacher. Today I'm going to interview Professor Manegiro. He is a physics teacher in Edison. He has been teaching physics for a number of years.
Very good. How are you?
I'm good, thank you. I know that you have been teaching physics for a number of years, so can you tell me how calculus is used in teaching physics?
Well, calculus is actually a tool used to explaining the working of the world around us. A simple way to look at, we live in a world where everything is changing continuously. A simple thing is, how does the position x of a moving car changes with time? Now, if you're standing on a traffic light and the light turns green, you put your foot down and go. Now, how does the position x of the car changes with time? It will be something like this, is that right? Now, if I ask you, what is the average rate of change? Well, average rate of change is defined in a certain interval where the position is x1 at time t1, the position is x2 at time t2. We say the average rate of change is x2 minus x1 divided by t2 minus t1, which we say is the slope of the secant line. But suppose you want to answer what is the instantaneous rate of change at that particular time. What you then need to do is make that interval very small. Make the interval very small, and in doing so, you can see your secant line will become smaller and smaller. And when that interval is so small that the secant line turns into a tangent line, then you have the value of, say, delta x divided by delta t in that limiting case when that delta t is very close to zero, that interval is very close to zero. That's what we call the limiting case when the delta t approaches zero, that value of delta x over delta t. We call that the instantaneous rate of change, or we call the derivative of the function x with respect to t. Now, this is something that we use widely in calculus because the rate of change is so common in not only in moving objects, in industry, in manufacturing, everywhere you will be doing the rate of change. Now, another application in physics is, let's say, a force vector moves through a displacement x. We say a work is being done. Now, if you draw a graph of the force vector against the displacement, if the force remains a constant, then that will be your graph. And if you multiply that force by that displacement, what you get is the area under the graph of force against the displacement. Now, what happens if this force is not a constant? Suppose that force is a function of x. Then the graph will no longer be a horizontal line. It will be something like this. Now, does it then apply the same rule? Well, if you consider a very small interval, like this, of very small displacement dx, during that time, we can say the force remains a constant. Therefore, the work done, dw at that time, will be the force function. Force is now a function of x. It changes with x. So that will be the force function multiplied by that dx. Now, that means it is the area of this rectangle. You can now take this small interval anywhere under the graph And if you add up all these dW's, you get the total work done. And this process of adding up or summing up all the dW's in calculus, we say, is integration. Integrate, put them all together. So we integrate all the dW. Integrate dW or fx dx will give you the total work done. A very common example where this is used in not only physics and engineering, in all areas.